So 1 degree anion is more stable than 2 degree anion. So 1 degree anion is more favorable in this case. Fine. Alright. So 1 degree anion is more favorable. So it's settled that base is going to abstract hydrogen from this carbon and not from this carbon. Fine. Okay. Now base has abstracted. A negative charge is there. It will come and form a bond, and this bond is going to break. It is going to come out. So when that process completes, you have one butene and N trimethyl is going to come out like this. So this one butene is the major product, and the one in which hydrogen is abstracted from 2 degree carbon, that would be a minor product. Fine. All right. So more than 95% of the product will be 1 butene, and 2 butene will be minor, that will be less than 5%. This kind of elimination has a name, and the name is Hoffmann elimination. Now Hoffmann and Sedgwick, there are two rules concerning elimination reaction. Let me quickly recapitulate you those two rules. Sedgwick elimination is the one in which after elimination the alkene is the most substituted alkene. For example, in this case 2-butene is more substituted butene, because if you see the number of alpha hydrogen, there are 6 alpha hydrogen here. 1 butene has only 2 alpha hydrogen. So as such, if you start to think from the point of view of ethene, then in this case you can say that in ethene this hydrogen and this hydrogen has been substituted by 2 groups. In this case you will say that in ethene only 1 hydrogen has been substituted by this ethyl group. So that's the way of saying that this is more substituted alkene, this is less substituted alkene. In other words, we can say that the alkene which is formed, that has to have more hyperconjugating structure, and thermodynamically that's more stable alkene. So as per Sedgwick rule, a thermodynamically stable alkene is formed, or a more substituted alkene is formed. As per Hoffmann rule, a less substituted alkene is formed, or a thermodynamically less stable alkene is formed, because in this case we are seeing that the stability of the final product is not as important as the stability of intermediate is. So we have written the product not from the point of view of stability of product, but we have written it from the point of view of stability of this intermediate of anion. Fine. So that's why Hoffmann elimination, because we are getting a thermodynamically less stable alkene, otherwise 2-butene would have been more stable. So this is as per Hoffmann rule. So this elimination they call as Hoffmann elimination. Okay. So let's solve a problem based on Hoffmann elimination. This is a starting material, and you have no dearth of this CH3 and Ag2O. You have many of them. So you can utilize as many methyl iodide and Ag2O as you can, and you have to get to the final stable product of this reaction. So I mean, work it out here on your own. We'll have a discussion, but try working it out. Now, okay, the purpose of Ag2O would be to generate hydroxide ion. Like in the last example, what we did, after generating quaternary ammonium ion, I added a base from outside. What will happen here is, as a reaction goes, as this nitrogen attacks this methyl and this iodine comes out, then this Ag2O will break down. When it breaks down, it generates hydroxide ion. That's the thing here. So this Ag2O is just added for the purpose of hydroxide ion. And one more thing, we are also adding heat in this reaction. If we don't provide heat, then the reaction will, the rate of reaction will be very, very slow. So we are adding heat to speed up the process. So let's see what will happen. The first step is simple. This nitrogen is going to attack this methyl. Methyl is going to come to nitrogen, and hydrogen is going to go off in order to make this nitrogen neutral. Again, you utilize more methyl iodide. This nitrogen is going to attack this carbon once again, and now you'll have a disubstituted cyclic amine. This time, nitrogen do not have any facility of getting rid of its plus charge. Okay, so the plus charge is going to remain there, and when iodide has come out, this Ag2O will break to generate hydroxide ion. So this plus charge and this hydroxide ion, this is what you're having in the system right now. I have not added a base from outside, so the concentration of these hydroxide are very less. So the rate of reaction will be very less. So we are adding heat for that purpose. Now you are adding heat. Now what do you expect? Now as we have seen just now in Hoffmann elimination, this base is going to abstract a hydrogen from alpha position of this quaternary ammonium ion so that this acts as a leaving group. Now see carefully. I'll remind you very quickly what we did. We have this leaving group, quaternary ammonium ion, and we were talking about removing hydrogen from alpha position. Now this is the carbon which is directly attached to this. The adjacent carbon to that is the alpha position for these. Now if you abstract hydrogen from these alpha carbons, then negative charge will appear here. It can go to this carbon and it can come out. So what you have to look at, the atom which is directly attached with nitrogen. Figure out that atom and you have to abstract a hydrogen from adjacent carbon. Then only C double bond C will be possible. You can't abstract hydrogen from this carbon because when this carbon gains a negative charge, it cannot give to anyone. On the contrary, if the adjacent atom develops a negative charge, it can send that negative charge to the adjacent atom, this carbon, and in turn, that can lose the bond with nitrogen and form a double bond with this carbon. So you have to abstract hydrogen from the carbon which is adjacent to the carbon which is directly attached to nitrogen. Fine. Now these carbons are directly attached to nitrogen. So you can abstract hydrogen from these two carbons. Fine. Both are symmetrical. The structure is symmetrical. So let's abstract from anywhere. We don't have to think about Sedgwick or Hoffmann. Both are Sedgwick, both are Hoffmann because it's symmetrical. So let's abstract a hydrogen from here. Suppose the base is going to abstract a hydrogen from this position. So what we are going to have, this is the negative charge, this is methyl, this is methyl. Now this negative charge is going to put its electron into the anti-bonding of this carbon. So a bond will form here and this bond is going to break. The electron is going to go into the orbital of nitrogen. So when this process completes, you have a methyl on nitrogen. This plus charge on nitrogen goes because it's taking electron. This carbon and this carbon are going to form a double bond. And this bond is going to break. So this is what you have. Fine. I told you there is no dearth of this methyl iodide. The nitrogen again develops a lone pair. So there will be further reaction and more methyl iodide is going to be attacked by this nitrogen.